Thank you, Ziyang. So yeah, I'm Romain. I lead the Cardano hashtags team. And this work that I'm going to present is very much not my work. I mean, I work on that, but it's a team effort, and we will not have this tool where it is today without like the whole team's effort. So I wanted to start by saying that. So formal verification of smart contracts sounds like a nice idea. I think everyone would agree that that's something that we should achieve. But when you start saying, well, we was going to write the proofs, well, then the end starts going down. No one wants to really write the proofs. It's really hard. And even more than if the design or the implementation is changing frequently, then your formal methods engineer that's writing the proof might become angry with the developer because he has to rework the proof all the time. And it's very time consuming, so it's not going very well. So that's why we want to automate formal verification. And like Ziyang said, yesterday we had a great talk by Theodore where he presented a way of doing formal verification of smart contract with those kind of abstractions, which is a great way to reason about like high-level properties. We're doing a completely different way. We want to be as close as possible to the implementation, so we don't introduce abstraction, which might sometimes introduce gaps between the implementation and the formal model that you've proven. And you have to be very careful that, those gaps don't exist. It might take a while. So I want to convince you today that hopefully in the near future, everyone will be able to do formal verification because it will be completely automated and you will not have to see any of the ugly details of what is formal verification. So our vision for the tool we want to build is fairly straightforward. It's straightforward to tell. It's very complex to implement, but we want the developer to be in their development environment, writing the code in the language they like, in Plins, in Icon, in Plots, Scalars, Plutarch, Opshin, probably forgetting a bunch of them, but like any language. We want them to be where they're used to writing their code. We then need them to write the specification, what the function is supposed to be doing, what the business logic of the dApp is. But then from there, we want to take care of everything and bring them formal verification. So they should just push a button and then get the results of formal verification, whether, yes, your code and your spec matches, so you hopefully don't have a bug, but at least on this specification, it's correct. Or no, we found the bug, we found a way to get into a state where you said something bad was happening, or we found just a transaction that's being validated by your smart contract that you said should not. So how does it look like? Well, first, the annotation. We need an annotation language, so it doesn't exist, it's just we came up with something for slides. But we will need to design an annotation language that the developers can use in their code. So here we just kind of put lean4 into Haskell by just having a special comment tag and say, well, that's where the spec is going to be. Might not be the final design, but it's just to give an idea. Then the developer just code their smart contract, so their validator. It's the escrow from the Plutus apps repository, if I'm not mistaken. And as I said, they just call our tool on this Haskell file where you have the code and the spec, and now we have to take care of everything. We don't want them to do anything and to get formal verification. So hopefully the tool will return either of two results. There's a third one, which is not the most pleasant one, but you can get valid. It means, your code matches the spec, you're good. You get falsified, well, you have a bug. And we want more than just falsified because, well, it's already a nice thing because if you have tried to prove something in a proof assistant, a theorem that was wrong, and just not obviously wrong, but subtly wrong, you might know that it's really annoying to find that why your theorem is wrong. I mean, to be convinced that your theorem is wrong, and you should not spend more time trying to write this proof because it doesn't exist, and you should fix your theorem. So already having falsified is great, but we want to have more. We want to be able to tell the developer, look, this is the sequence of transaction with those UTXOs, with those inputs, with those datum and redeemers that led to a state where you have something bad that has happened, like you reached a deadlock, or you said, well, no one can steal the liquidity. Well, someone stole the liquidity. OK, great. but like how do we do that? It seems, I mean, that seems like the ideal tool, I think, for formal verification. And how do we build that? Well, first, as I said, we need to be at the level where the developer are. So we need to be able to take the annotated code. Can you see my? OK. Their annotated code in their favorite VS Code or where Emacs, wherever they build their VS Code, their code. And then we need to bring that into a formal language where we can reason about everything. So we chose Lean4. So we need to be able to transpile their code from Lean4, from their surface language, so Plins, Icon, Plot.ts, or even UPLC, and translate that into Lean4 so that we can then start to reason about. So that's the goal of the transpiler. The transpiler just bring everything about the smart contract into Lean4. So at that point, if you're brave enough, you could start doing formal verification. You would just have to do it by hand and explain a lot of things to the to Lean4, but in theory, you could. You would miss probably one thing that will help you a lot is everything, because at that point it's in Lean4. Lean4 is not a tool for Cardano. It's just proof assistant. It's built to do proof of theorems for math or for anything you want, but I mean mostly math. So you would need to put into the tool what is Cardano, what is the blockchain, what are the ledger rules, what are the built-ins, what do they do, what is the CK machine, what are the ledger constraints, and everything. That's what we need there. We need to, and what we have to build and what we're building is putting basically everything about Cardano in Lean so we can reason about that. An answer there, you could really start proving things about your smart contract in Lean4. Once again, you just have to do it by hand, which might prove to be very time-consuming. So this is where we building what we call the core kernel or the reasoning core, or now we have kind of a name for that. It's called Blaster. It takes your Lean theorem, what you're trying to prove, and your code, and it's going to optimize as much as possible your problem statement, like your theorem, by removing some, I mean, not removing just for the sake of removing, but finding that some branches are not reachable, so it's going to remove those. Finding that you have constant that we can propagate, so it's going to propagate those. Propagating function, doing a lot of things, but I'll show you a few examples. But the idea is we want to bring these very complex things, which is the CK machine, ledger rules, built-ins, your own code, the theorems you want to prove, which make a very big model, and we want to reduce it to an equivalent one, but we want to reduce it as much as possible. And once it's been reduced, you can also still do from there proof by hand. But once again, we don't want to do that. So we have to send what's remaining to something that will solve that remaining theorem for you, which is we picked SMT solvers who do automated reasoning. So we translate into a language for the SMT solver, which is called SMTlib, and then we ask a solver. We say, well, we have this problem. We need to know if it's true or not, like if my theorem is true or not. And those SMT solver can produce the results that we were expecting. So either valid, it says, yes, your theorem is valid. It can find a counterexample. It says, no, look at those values. If you input those values in your theorem, you will find that it's not true. And as I said, there's a third branch because basically what we're trying to solve as a problem is undecidable. So you can't expect to have only those two. We have a third one, which is basically undetermined. And determined can come from a lot of reasons. Either the solver will tell you, I don't know how to reason about what you've sent me, so I will not even attempt. Or it seems that it can solve it, but it's just going to take forever, and you will reach a timeout. That's why you have this third branch. And what we want to build for more UX, I mean user experience, is we want to build a VS Code extension that will take those very, very dry and raw counterexample, which is just valuation for values. So it will give you values for a bunch of things in hopefully kind of ordered way. But we want to grab that and bring it back at a level where the developers can understand what's going on. So this trace of transactions, for example, because we know what problem we're solving. I mean, we know the application of these tools, so we know it's going to be for Cardano smart contracts, so we can probably rebuild those transactions. So let's go through some of the steps. The first one is optimization, simplification, and SMT translation. It's really the reasoning core where we automate the formal verification. So all of those steps are like the cornerstones for scalability. If we would take the problem as it comes, so the code with the annotation and the blockchain formalization, just translate everything to SMTlib and says, well, automated prover, do your job, tell me if it's true or not, it would just never work. It's too big, the solver will probably give up, reach a timeout, say, or just not even attempt to solve that. So that's why we need all of those steps. We need to reduce the internal representation of this problem as much as possible before sending those pieces to the SMT solver. And that's really how you remove the need for a formal methods engineer to build your proof, is by minimizing as much as possible and helping the SMT solver do its job. And from our experience, and because we are always writing new optimization, new simplification rules, we see that this what speeds up the proof time or the solve time dramatically. You can say, well, the solvers are going to get better, so I'll just use the next version, and it will be slightly better. But if you really want to speed up or scale up to the size of problem we have to solve, you really need to be very careful on and to put a lot of time on those steps. We have a bunch of optimization. We do, as I said, we do constant propagation. You realize some stuff are constant, so you're trying to propagate them as much as possible. And if you're lucky enough, you will have a constant, for example, added to another constant, so you can reduce that to one constant, and you try to propagate through the branches everything as much as possible. Same for all kinds of operation, on proposition, on Boolean, on some arithmetic rules, on a bunch of types, natural number, integer, strings, whatever. We need some optimization rules to be able, once again, to reduce this complexity. And then more complex one on ifs and else's, match are where we have a lot of optimization rules because, yeah, we want to, if you have a large match, and there's one on my back, like the CEK machine, you really want to be able to say, well, those branches, they don't matter because it's not going to be explored by this particular UPLC code. And we handle recursive function. If we have equivalent, and we do a lot of equivalence detection where we say, well, that function is the same as that one, or that expression is the same as that one. So instead of even trying to optimize them separately, I can just detect they're the same optimized one and propagate the optimization, and hopefully a lot of things are happening. So we have a lot of optimization, and I'll show you later on some examples how much it reduces the complexity. And then we have to encode to SMTlib. So it would be easy if they were kind of the same level of logic, but Lean4 is much more expressive than what you can put into SMTlib. So we have to find all kinds of tricks to make the SMTlib representation equivalent to the Lean4 definition theorems that we have to prove, and we have to encode in a lot of ways what we need from, what we are from Lean4 into SMTlib. So recursive functions, inductive data types is a very big one, but then you, as I said, you get some things that are not like naturally supported. I mean, they are supported by SMTlib, but you have to be a bit smart about how you do higher order function or even just parameterized type. That's one of the hard thing to do. But once you've done that, then you're good. You have the whole pipeline. And let's see a few examples. So maybe I'll just start with some very simple optimization rules just to give you a feel, and hopefully everyone can understand the kind of things we're doing. So here, I'm not going to show you, I could show you the optimization rules and how we implemented them, but I think it's a bit easier to understand on examples. So it's very simple here. We're in optimize EQ. So we want to, when we have an EQ operator, we want to be able to reduce it to something hopefully simpler. So if we end up to something where it says false and true, well, we don't really need to keep all of that. It's just too much. We know it's false. So we can replace false equals true by false. Same way, you have true equals false, we can replace it by false. And it applies in a lot of cases and a lot of operation. Like if you have, if you're wondering if A or A is equals to A, well, we're going to reduce to true. We don't need to, because we don't need all of that. We don't even need A anymore. So that means that when we would translate to SMTlib, A would have disappeared. So we don't need an extra variable. We don't need an extra quantifier. We don't need an operation on OR. We can just replace to true. And since it's true, well, we don't even need the SMT solver in that case. I can then show you a few still simple, kind of simple ones, but if you have those, and they show something that I didn't mention, but so if you have something like for all x plus y, you wonder if x plus 0 is lower than y. Oh, sorry, yeah. Oh, sorry, Anna.
Sorry. Just want to ask you, can the user easily add such simplification rules?
Not yet. But what we want to do is to be able to say, if you give us a theorem that is basically a simplification rule and a proof, we want to be able to add those into the... So if you add a lot of them, it becomes a bit slower on our side because we might have to decide which one we want to apply if there are several that are conflicting. But right now, it's not super easy, but we want to make that easier, yeah. No, good question. So for that one, x plus 0 is lower than y. We can just transform that to not y is lower than x. Why we introduce the not is because we want to have a canonical way of representing everything. So we reorder a lot of variables. We always try to go through the same operators so that when we do those equivalence checking to check if two expressions are the same, if they are in a canonical way, it's much easier to detect that they are indeed the same, and we don't need to prove that they are the same. So great. We have optimization. I mean, I can go through maybe another one when we have those. For example, if then else and match are one where we have a lot of rules because that brings a lot of complexity if you don't handle them. So for example, you say, well, for all C, which is Boolean, and A, which is just a proposition, if I have something that is if C, then A, else A, well, I don't need the if, then else. I can just say I want to prove A because both branches lead to the same thing. So that might seem silly as a rule. You say, I'm never going to code that. I never have that in my code. For sure you will. I mean, I hope you won't have that. But you have to realize that those will happen not in your code, but when we try to prove of other optimization, and especially if when we try to prove that your code matches your spec, we might get to those silly rules where we just say, well, both branches are A, or what we had earlier where you have like A equal A, then you want just to say true. It's because maybe one of the left side was your code and the right side was the spec, and we just reduce them so much that it becomes is A equal A. So all those rules just in isolation doesn't remove a lot of proof. Like if you want to prove that by hand, it's not going to be hard. But if you put all of them together, and we have a lot of different kind, and in each kind of optimization, we have a lot of rules. When you put them all together, that's really when you can see the power of the tool. So let's do a few simple things. Maybe not all of them. I just grabbed a few ones from the lean natural number game, which is a way to learn lean. You basically have some very simple theorems, and when you're learning lean, basically it says, well, how do you prove that? And you have to write a proof. It's probably like 4 or 5 lines, nothing too hard. But instead of doing that, you can just call OR tool. Because the reasoning core, if you forget about the Cardano brick, it's just something to solve lean. So we can just call the tool and see, yep, it's a valid theorem. It just says valid. It has translated it to, it has taken this expression, optimized it, and probably ask the SMT solver. We can quickly check, only optimize. Yeah, okay. Yeah, it needed the SMT solver. So it sends something to the SMT solver, and the SMT solver said, yeah, this theorem is valid. Then you get a more complex one. I don't know what you're trying to, prove that B, because you have A equal times B. Yep.
So just a quick question, because most people is not familiar with how to develop with lean. Why did you see that it needed to send SMT?
It's because when I do only optimize, I'm basically telling him you can't send something to the solver. You have to just rely on the optimization step to see if it reduces to true. And here, the fact that it didn't manage, it says here unsolved goal, or it's in red. It says, well, I didn't reduce to true, so I need to send to the SMT solver. Oh, thank you for the question. So, I mean, I barely have to look at the theorem. If I want, I can just ask the tool if those theorem as true, and instead of writing a very, well, I mean, not long proof, but I can just ask the tool. And, okay, you might say, well, your tool always returns okay, so it's super easy. I can do that in a line. But if I modify something like, I'm just going to change that to an F. It says, oh, wait a minute, no, that's false. And you can see if you put those values in, you will see that your theorem is false. So basically, it can help solve theorems automatically. It detects counterexamples. So instead of trying to prove that where you just mistakenly put F instead of E, you can just get a counterexample, analyze the counterexample, realize that, oh, I know, big mistake, you fix, and the tool will tell you, yeah, it's fine. Now your theorem is proved. Yeah, and for all of them, and a lot of the, I think we solve all of the lean natural number. Yeah, Ramsey?
So the blaster says yes, can actually give you a proof in any readable sense?
Okay, that was one of the my last slides. No, not yet, not yet. We are working on that. This is called proof reconstruction. Basically, what we're doing right now is for each optimization steps, I mean, we were tracking what optimizations we were doing, but we're producing an equivalent tactic in Lean to be able to reduce. And then one thing we will have to do is from the SMT solving part. So when the SMT solver would say, yeah, we'll say us unsat, if you know SMT solver, which basically means yes, it's correct. We want to get what's called the unsat core, which is an explanation of what the solver thinks your theorem is correct, and we want to write a proof from that. So right now, no, it doesn't, but
So Isabel's sledgehammer, sometimes it's unreadable, but at least it tells you which rules it used, and you're like, oh, okay, it used to do something, that makes sense. But
no, here we want to produce a full proof, and we want to be able to because if you change something in your definition above it, we'll have to recompute all of the proof, and sometimes the call to the solver can be very expensive and long. So we want to store the proof to be able to say, well, before calling the solver, try the old proof, maybe it will work. Yeah, Anna?
So, how do you deal with recursion? I saw that you have some inductive proof schemas.
Mm-hmm.
But I guess it won't work for every program. So
No, it won't. No.
is there a way for users to add inductive rules?
In our optimizations or?
Well, yes.
No, the user right now can't touch anything on the reasoning core.
Okay.
So if basically if the tool tell them, oh, I don't have the inductive schema for that, well, send an issue or write a PR, but you can't add what's necessary easily. But I mean, I probably have somewhere some recursive function because we handle those. It just, yeah, if it's truly unbounded, it's difficult because if you're trying to prove the equivalence of two inductive functions, or yeah, recursive functions, sorry, we might be able just by detecting that the body are the same. And I think I have one example that I know where it lies. I think it's in. I think we have the equivalence with NatPow. Optimize recfun, probably around here. So we redefine our own power, just for fun, and we want to prove that it's equivalent to the natural, the one that comes with Lean. And we do that by rewriting the, because also we don't use the mul from Lean, we have our own mulnat that we're re-implementing, so it's slightly better, and also add, so everything is kind of different. But by those rewriting rules, we are going to detect that they are equivalent. So if you write this theorem is power nat always equals to NatPow, it just reduces to true because we are going to detect that the body is the same, even if the names are different, even if everything is different. So we normalize everything. We realize that they're the same body, they're called on the same arguments, so we can just say, yeah, they're equivalent. But if it's not that straightforward, there might be some issues here down the line. Yeah?
So I'm not super familiar with Lean, but as Ramsey asked, right, so when you call Blaster, you can't really get a proof out of it, right? But what does it actually give you? Because so like you're plugging it into this place where I would expect Lean would expect a proof. So
Yeah.
what exactly does Blaster return?
It returns, okay, so if you want to go in the details, it returns, if our solver finds that the theorem is valid, for the moment we have, we're just returning admit. I don't know the AGDA equivalent, it just, yeah, trust me, bro.
Okay.
And if it finds that no, it's not valid, we fail the tactic, and we return the counterexample.
Okay.
So, I mean, you can do something. You can say, well, just optimize, because maybe the SMT solver is not being able to prove, and you can finish the proof by hand if you want. So, and that one, okay, no, that one would be completely correct, because only optimize, we just optimize, and it's equivalent, and it can detect that we just have equivalent goal at the beginning and the end, and then you finish the proof by hand, and that would make a valid proof in Lean. All right. Which one do I have? Okay. So yeah, great. You might say, well, that's really cool, Romain, but you spent a year or even more than a year with the whole team to build something that can prove some very easy stuff about math. So let's first compare with what everyone else is doing. So we recently got this benchmark from a collaboration we have. It's very nice. It's in Lean, so everything is in Lean. But the idea, there are several things you can compete on: code generation by LLM, spec sound incomplete, where from a natural description you just try to generate the spec, and also try to generate the proof. And so it's very much a comparison against LLM, so not completely fair. But I have then one against other tactics. So on those verification objectives, which are kind of, they look like software verification with precondition, a function, postcondition you want to prove. The best LLM is O4 Mini, surprisingly, but it's O4 Mini, which solved 3.6% of the overall benchmark, and Blaster scored 15.3% of correct solves. And we didn't, I think, well, yeah, we didn't optimize for benchmark. I mean, you should not optimize for benchmark, but there are some stuff that we don't support that we could support very easily. Just it never came when we were trying to prove UPLC. And by adding just those support, I'm not saying we would solve all of those problems that use them, but we could at least compete on 50 more of the programs where we just say, right now, we just say, well, unsupported type, please go away. And on the Lean book, which compares some of our other tools that do SMT solving or try to come up with a proof. So like Lean Hammer, Grind, Canonical, ISOP, and LLM, we can see that they have a much better rate of success. The best one on the kind of classical is Lean Hammer, which has 80%. The best LLM is Schema Prover with 4 pass at 87%. And we scored 81.77%. And once again, we didn't optimize for the benchmark. So there are, once again, some stuff we don't support, like types. We don't support, like fin, which is just finite integer, or bit vector, because we never met them during UPLC. So if we had support, we could maybe not reach 90%. We would have to do something more. But like we think that 90% is very much achievable.
Sorry, you said the Lean book. There are lots of Lean books. Which one?
I don't know. I was just given a collection of problems, told it comes from the Lean book, and I just called Blaster on everything. I have the example. We can look and figure out which book it comes from.
We can just Google it.
Yeah.
And why does one of those not add up to 100%?
That's a good question.
I think it times out.
Maybe, yeah.
Maybe
On those. This one, I don't know, yeah. I didn't do that benchmark. I just grabbed and.
Those are LLM proven?
The top one are LLM. The bottom ones are classic Lean strategies through SMT solving or some other forms of reasoning, automated reasoning. But they're basically automated reasoning, yeah. It's when you don't want to run a proof, you call grind, and hopefully it will work, but you can see it's only going to work half the time.
I'm referring to this as good old-fashioned data.
Good old-fashioned AI, yeah. So I showed you a tool that can solve math, which is, I mean, not solve math, but some math, which is okay. But if we want to solve and prove some things about smart contract, we have to, as I said earlier, we have to explain what is the Cardano blockchain. So we are there. I just showed you the core kernel, optimization linked to SMT-lib, call to SMT solver. We get some good results. But now we have to implement all of that, which is a lot of work. So the idea we had is that we want to implement like all the libraries. We need them in Lean because otherwise we can't do anything about that. So the first thing we started to do was to implement Prince libraries. And we wanted to be as close as possible at the original Haskell implementation by the Plutus core team to be able to say, yeah, when we're proving something in Lean 4, we really are proving something from the Haskell one just because by traceability we can see they're the same. So we re-implemented everything, so it looks slightly different, but it's still functional programming. I mean, it's not very readable, but it's, I mean, hopefully you can see that we're fairly close to our Haskell implementation, and that's one of the odd where we are the furthest away from the Haskell implementation. So the only thing we do is that for the odd instance, we need some properties to be able to reason about when you get something and to be able to have correct rewriting rules. So we added a few properties about the operation on odd to be able to reuse them during the proofs automatically, or to be able to reference them when we're having those rewriting rules. If you want to change from a greater than to a lower than operator, then you need to be careful, and it's not very hard, but at least now we have a proof that it's a correct operation, and we can do that for any type that has an odd instance.
So those rules, Romain, they look awfully like the compilation rules in Haskell for the classes.
Mm-hmm.
So really, what we seem to be doing is to formalize the compilation rules, the semantic.
Yeah, but for example, EQ doesn't, I mean, they tell you it's nice if you have some of the properties. At our level, we're forcing you to be reflexive, to be transitive. Yeah. And we say, well, it's not really an EQ instance if you don't have those, right. Because otherwise we won't be able to do much.
Yeah. That's something you can't do in Haskell because you don't have the semantic notion, you only have the syntactic notion.
Yeah. So we're doing it. And same for everything. So Plutus core, we are formalizing data, we are formalizing everything we need. And also, again, we're writing some properties of kind of correctness, just because we want to see if our implementation is correct, but also because, once again, those properties about data will be used afterward in the optimization step that we have. And like it seems everybody in this room, we re-implemented the CEK machine in Lean. So I wear the CEK machine on my back, and I checked it looks correct. So I'm very happy, except you added a case. So I need to add that to the machine. But this is not just a screenshot from the spec. It's the one that I just took from our Lean file. So I had to do a lot of prettifying with macros so that it looks exactly the same. Jean-Frédéric hates it, but it's the same. So we're happy with that. All right. So now, great. I didn't show you much, but you can see that we have something about the blockchain. Let's go do one example. So one thing I didn't show you is that, but I told you earlier, we need to be able to import from the file because we want to be proving what the developer is doing, and we don't want to have an abstraction unless we really need it. But if we don't need an abstraction, we don't want an abstraction. So what we can do is that we grab the UPLC programs. So I think I wrote that by hand. It's not from a compiler, but I mean that's a UPLC program that just add two integers, x and y, that you pass to lambdas, and we built a parser for that that just grab the UPLC, parse it, and then produce an equivalent Lean definition that uses our formalization of UPLC. So if we, oops, sorry, I close that. If we toggle the info view, you can see that now I have this UPLC, and now I have this definition in Lean, which is which looks very much like the UPLC program. Just now, it's Lean. It's a Lean object, and we can reason about that. What we do is then we push that program, that UPLC program in Lean, 20 times through the CEK machine by giving it two integers, x and y, we execute an int program, so why do we have to do that? I mean, it's kind of a hack right now, but we will do something better. It's because at the end, we want to be able to extract the last term and say, oh, okay, it should be an integer. You should see an integer. Just give me the integer. Don't give me the whole term. I don't want that. So it just that way it can return an integer. And we can write specs. So we can say, let's not do the one first, but let's do the natural one. You want to see that if this program, when you run it on 2 integer, actually produces x plus y all the time. And you could do that by hand. You could say, well, I'm going to unroll the steps of the CK machine one by one, match on the cases, say, make the tool realize, make clean4 realize which branches of the CK machine it's using, propagate some constant, do some formal verification trick until I get the proof, or you can just call Blaster. And it's going to, yeah, that's fine. And if you, once again, because I could just, I think it's subtract integer, I mean, we can just reload. I change the program, and now it's telling, no, wait, no, you made a mistake somewhere, because when I'm running this through the CK machine, I don't get x plus y on some example. And you can see that by just having x equals 3 and y equals 2, it's somewhere. And you can eval on that and see, yeah, it's returning 1 because, I mean, I just changed the built-in. I don't remember. Don't restart file on Mac. So, okay. If you want to you can have also all kind of property like, is it commutative? So you're just wondering, does running this program on the CK machine always the same? If you flip the arguments, once again, you can write a complex proof, or you can just call Blaster. And as kind of a show-off, I can show you that we don't even need the SMT solver. Just by the optimization rules, we are optimizing everything about the CK machine away, and we're just producing true at the end. And so, I mean, I can show you. Wait. If you're curious, execute. I want the second one. Can we just check the lin file? Oh. I don't. Oh no, I think this one also optimizes everything. Yeah. Sorry. I can fix it quickly. Sorry. That was equals sum equals r dot. Yeah. So if you're curious how it looks like, so once again we have this UPLC program that we get into lean, and then we push it through the CK machine 20 times. The resulting SMT query that we send is rather short. So all of this part is just setting the solver. This is declaring the types that we need. Having some information about the type, declaring constant, declaring data type, declaring function, and then this is just your program running through the CK machine with its spec, and that's really what we're asking. So the optimization did a lot of work, and we can even see on this other correct spec that the optimization does all the work. And, well, yeah, I mean, you're probably getting it. If you want to know if something is true, you can just call Blaster instead of writing the proof. How much time do I have left? 20 minutes? OK, I can show you a few more examples that are kind of cool. So this was a toy example. I'm not going to pretend that that was a very big example. But we have this compute setting token that comes from JED, which is used in production. And that's a bit longer UPLC program. It's 326 lines. We have even larger one, but on this one we have a really cool example. So the V1, if people are familiarized, can guess which language was used by the names. So it was written in Plinth. And we can import what the compiler gave us. We have to do a bit of work in shaping the inputs correctly. And since it's not a validator, it's a function used in a validator, there are some preconditions. They know some stuff about when they're going to call this function. So we have to also specify that. But then we can start try to prove some things about this. Oh, that's not the right one. About this program. Sorry, I'm not on the right file. This is the second part of the demo. SMT, benchmark, UPLC. Look at the other ones on chain. Okay, I'm going to show you process SC order. It's the same thing. Except on this one, it was before we had this parser of lint. So here we did it manually. So it's a bit longer. It's a long UPLC file. It's 820. I mean, there was the header, so maybe 800 lines, and then we have those properties that you can start to prove. Not this one times. Sorry. No. Oop. Yeah, this one we grouped. Oh, sorry. Yeah, I know what we did. It's not the right branch. Oh, sorry. So we can write. Okay, I'm going to show you with the hand, and then I'm going to go back to the other example. We can write properties about those ones. And here, Jean-Frédéric on this branch recently grouped everything together to see if we could do case splitting. We can't, so we don't have the proof. But you write proofs, and then you call Blaster as your reasoning tool, and we can prove some things about that. Here it looks a lot less impressive because we have to write all these.
Some things this is very specific.
We can prove the spec. We can prove the spec, but here we have to use. We have to.
Spec for this program is true. That will be easy to prove. Can you say something about the
Yeah. So.
program is?
The program is another function used in JED. That's the one that was there. So it processes a stablecoin order. So on JED, when you want to buy a stablecoin, it's going to call that function that I can show you because there are so many tabs. But it's going to call that function somewhere, and they have the spec of that function.
Okay.
And so we have the UPLC.
One example of a property in the spec that it proves?
And then we write the spec of this function, which is if you have a valid input, if you have a valid order input, and you compute the result you're expecting from the reserve, because you're buying a stable coin, it's going to be some S, and you want to say that the reserve is again valid after you've processed the order and got your S tokens.
Well, what do you mean by the reserve is valid?
Oh, yeah. We can go there. The reserve is valid. Why is it not finding the definition when you can prove it?
An intuitive explanation is.
One of those is going to be, JED has to have this reserve within those bound 400, 800. So that's one of the properties that you want to verify.
The algorithmic stablecoin property of the reserve.
Yeah, that's.
Can only fluctuate within certain values.
So here we actually have. So here, Jean-Frédéric grouped everything together, but we used to have, I should have checked that, that for each of those requirements that the JED reserve can never, is always non-negative, that you have a non-negative number of smart contract, SC, stablecoin, that you have a non-negative number of reserve coin, and some other properties about the backing of stablecoin, and the backing of reserve coin. All of those used to be separate theorems. You can just call Blaster on each of them. It will prove. Here we grouped everything together. It shows you, if you're a formal methods engineer, that you can still write proofs, even if they're too complex for the solver, and just call Blaster on some of the cases, and it's going to discharge them. Here it's going to take a very long time because some of the things we're sending to the SMT solver are really big, but it will eventually finish. Yeah. Let me go to the, sorry, but the compute setting token has something that is super cool, so I can go back to that. So the idea was, so they wrote this one in Plins, but they found out it was not optimized enough. So they wrote another one, a V2, and I have it somewhere on there. You can see from the name of the lambda that it might not have been written in the same language, and it's not even the same encoding of the inputs. And what we want to prove is that, the engineers pretend in this PR that it's just an optimization. Trust me, everything's going to be fine. And you want to see if that is indeed the case. And so it's the solve command. You can write a theorem, but it's a solve command. So what you're just writing, the same of the command you've seen, just as a command, not as a tactic. It has a much nicer output, but it's the same. So you say for all input, which are valid, you want to see if the V2 always output the same thing as the V1. As UPLC program running through the CK machine, and what's the bound we put? 20,000 times at most. And we cannot even prove that's enough for this function to always terminate. And here the solver will tell you, wait, no. use these values, so whatever they mean, and you will see that your V1 is not equivalent to your V2. And we send that to the JET team and say, oh yeah, you're right, we forgot one case. So they produce a V3, again in Plutarch, and they said, well, that one should definitely be true, and we can prove, oh, I don't have theorem. Let's write it. V3 is always the same as V1. Oops. Oh yeah. What is not working? Oh, sorry. It was working. Maybe I changed the files, but you can prove, the same way we prove that it's not equivalent, you can prove that they are equivalent. And I was thinking about that when we had the UPLCK presentation, which was really good. And instead, you could prove that when you submit a new submission, that the UPLC you get is either matches the spec of what you wanted, or is equivalent to what you have as also submissions. Although I have it there. Okay, yeah, no, because you need to be a valid input. So yeah, so if your valid input, you want to prove that compiled V3 is always the same as V1, you send that to the solver, and it says valid. It's just if you don't have a valid input, it finds counterexample, but it was optimized for valid inputs. Okay, no, so I have it here. And once again, we're proving the UPLC directly through the CEK machine, and not something that could be an abstraction, and we're doing it automatically. And then you might say, well, I don't want to write proofs. I don't want to write proofs, but I don't even want to write theorems. And okay, we get that. And I want to show you one example that we did from Icon. So someone, I don't remember the name, but built and flattened directly in Icon, a flat library. And in those, you have those properties, zigzag and zag-zig. And the spec says that when you do zigzag and zag-zig, you should, it's basically the identity, and same if you do zag-zig and zigzag, it should be the identity. And so they wrote those tests, and they said, well, we don't have formal verification yet, so I just want to use the fuzzing library that comes with Icon. So I'm going to say, well, X should be fuzzed between those bounds, and I want to see that this test always returns true. And same for the other way around, except the bounds are slightly different. You need to be a positive integer. And you want to prove that this test is true. But the nice thing about Icon is that everything compiles to UPLC. So this test compiles to UPLC if you want to. And instead of doing fuzzing, we can do proofs. So, and you don't have anything else to say. You just say, well, my proof test is just something that's going to say you should have a Boolean at the end, and we're going to extract the value of the Boolean of running the test through your UPLC program through the CEK machine. It should always be true, no matter the input. And that would be just a much better version of fuzzing, because instead of hoping you find the bug, you can just say, well, and yeah, it's true. So your test will always return true, no matter the input. So you don't have to fuzz it. And you can even prove that this one says it's always terminate, because proof tests extract a Boolean if it looks like a Boolean at the end, otherwise it's going to return a none. So you say, well, it should always be a sum. So are we always terminating? You ask that. Yeah, always terminating. The other way around, zigzag-zig. We call blaster, says, yeah, your test is always going to be returning true, and is also always going to be terminating. And since we're in formal verification, yeah, they need it bound because, well, they need to fuzz between bounds, otherwise, they don't know how to generate. But we don't need bounds. We can prove that it's even true without any bound. And we can just prove that this zigzag-zig is always the identity, no matter the input, even outside of those bounds, and that it's always terminating. So if you're writing tests, fuzzing tests in Icon, we can just call the tool on those, and instead of fuzzing, we can just check for every possible value. And if it doesn't pass because the solver doesn't like it, you can always fuzz it and see, okay, I couldn't prove it, but at least I can property-based test or fuzz it.
That's great.
Thank you. How much time do I have left? Not that much, I think. Okay. Yeah, I just showed, I'm going to go a bit more quickly through those. I just showed how we can reason about one call to a function or one validation of a smart contract. I didn't end up showing a smart contract, but it will be the same. You have your UPLC, you write how you should format your input, and then you write properties about your smart contract. But if we want to reason about traces of execution like we want to, we have to build those states. We have to build the blockchain as a state machine from a ledger state to a ledger state through a blockchain event. So a transaction here, it's very simple, just transfer of value. You have 3 UTXOs and input. You produce 2 UTXOs. And so your blockchain is being modified. But we have to explain when that is valid to the solver. So we have to write what is a valid transaction, what will the ledger accept as a transaction, what are all the rules so that the solver can know how to do that. But if we do that, and we're doing it these days, we can then reason about traces of execution, which is much better because you can say, well, starting from an initial state that I think is valid, I want to see if no matter the trace of execution, I never have this bad property. Like in the JED one, you want to say, no matter the traces of execution, I want to see that the reserve is always valid. Or if I could, or the order will always be able to go through, or any kind of property you want to verify. But having a trace of execution is nice, but it's not enough. You need to have all possible traces of execution, all the forest of execution from all the possible initial states, going slowly through all the everything that can happen. So if we take the JED example, you could say, well, someone can buy JED with buy some JED with whatever value, or they can buy some reserve coin, and then they can sell that reserve coin, or buy more reserve coin, or buy some JED, and user A, but also user B or user C, and so on. So this figure doesn't do it justice. There are much more states than those ones. We don't start with 3 initial states. We will start with probably uncountable a number of states, and each time you consider all the things that can happen, it grows exponentially. So that might seem like a dead end. I'm never going to explore all of those. But I'm not going to explore them one by one. I'm going to do the same trick as we did when we were, for example, representing integer. We're not doing the test one integer by one integer. That's crazy. It will take too much time. So we grouped everything into formulas. We group everything into a formula that explains what is an initial state, what is a valid state 1 that you can reach from a state 0 that is a valid initial state, and so on and so forth. And then we have this part of verification. We say, well, we ask the solver, can you find me a state S3 where the property is not true, so that it will give us a counterexample. That's basically the idea of bounded model checking with this one formula, which is big. If you look at it, it's going to be massive, but the solver can handle it. You can get a trace of execution that leads to a state where your property is not true, where something bad happened, or maybe the solver will say, I cannot find one of those S3 where the property is not true, and then you're happy because you know that any trace of execution of length 3 is safe. So it's very fast, actually. The formula is big, but it's still fairly fast. But it's incomplete what happens at the 4th step of the trace. We don't know. I mean, you can build the formula for 4, but it's just going to push into the future when you don't have the proof that your system is correct. So there's another technique, another proof strategy, which is called K-induction, which is basically induction. And you want to show that if you start from a valid state and you go through only valid state for a number of time, here it's 3, so it's 3 induction, you will always have your property on the last state. So you want to show that if you start from a state where everything is safe, and you do only valid transition, you will always reach states where your property holds, where everything is safe. And just by induction, now you've proven that for any length, you have to prove the base case. But you prove the base case, you prove the K-induction, and now you can have that your property holds for any length of traces of execution, but also for any traces of execution. So you've really proven that no matter what will happen to your smart contract, it satisfies all its properties.
Sorry?
Yeah?
Why don't you just prove PS0 and PS0S1 implies PS1?
No, yeah, that's the first step.
Well, then it might not be, because it might be those short traces that are invalid and you have to take 2 steps to get back to a valid one.
So you start by trying to prove...
No, because you're also saying that S1 is valid.
No. If one step gives you a valid state for any valid state,
Yeah.
then that gives it to you for everything.
Yeah.
Sometimes you would do this without the PS1 and PS2. So
Yeah,
you transition through an invalid one and
No, I mean,
Yeah, that's not what
what you're saying, Phil, is true. We would try one induction first, because if that proves, then we have it. But it's very rare that something is one inductive, so you have to unroll that a bit.
Oh, now I understand.
And then you prove that you use BMC to say, okay, but any beginning of a trace of length 4 is safe, and then you plug this kind of longer K induction into that induction proof, and now it shows for any trace. But if you prove one induction, it's great because you have less work to do.
But, so the formula you've given
Mm-hmm.
asserts that every state you hit is valid.
Yeah, the first 3 ones are
What
valid.
he was saying is you might have an invalid state in between.
Yeah,
You might want to show that even if you have invalid states in between it, you still
It's
have valid states.
depends what we mean
But
by
this
valid.
is just showing for valid states. And
all valid states,
the
yeah.
shorter thing I gave also proves it.
It proves it, but sometimes the solver will not be able to prove the one you have. You can help the solver, because I mean it's not because the solver is bad. It's because your property is not. I have an example. I have 3 minutes. I can show you an example of something that's not one inductive, and that is 2 inductive. I mean it's built for that, but it's going to be in state machine and bull flip. Remove that. What do you mean? No. Max depth 1. No, I need to remove that. So you have a state machine. It's a very simple state machine. You should be able to go through. You have 2 Boolean, A, B, and what your state machine does is at every step it just flips. A is equal to not A and B is equal to not B, and it repeats over and over again. And you want to prove that you never have A and B. So you want to prove that you have not A and B, which is okay because you start from an initial state where A is not equal to B. So one is true, the other one is false, and you always flip them. So this invariance it seems reasonable. But if you try to prove it with just one induction, what you were mentioning, the solver will say, no, I don't know why, because I can have the state where I have A and B that are true. And you want to say, well, no, that's not possible. But the way the K-induction property is written, it just says that at the beginning, you just have your property that is true. And if you have A and B which are true, then, no, false, should be false. Where are we? Oh, yeah, no, false. A and B are false, sorry. A and B are false, so you have your invariant that's satisfied because A and B is going to be false. You take the negation, so your invariant is true. But that state is not reachable. You cannot reach false and false because you start from true and false, and you always flip. And one induction is not enough to see that this state is not reachable. But if you do, and surprisingly, it looks very much like things repeat, like you have a pattern of length 2. But if you say, well, you can do 2 induction now, it's going to say fine, because it realized that the state false and false can never be reached. You cannot have false and false in any trace of length 2, because that's never going to happen, and then it is able to solve everything. But we can discuss about that. I just have like 1 minute to go through everything we want to do. So current state of the tool, you basically saw it, but what still needs to be done is a bit more interesting. So we still have a lot of Cardano formalization to do. We have built-ins to formalize. We have the ledger rules that we want to formalize. We have this blockchain state that I've shown you with those UTXOs and much more information that we still have to build. We also want to have a better lean SMT backend that can be used by people that are doing something else than proving smart contracts. So we saw that in the benchmark. We need to add support from other types and other lean constructions. A lot of them are not really hard, it's just time consuming. And yeah, we didn't need that for UPLC so far. A lot of the optimization rules, Rob will probably disagree. I mean, not disagree, but he sees this objective PI after PI that we have to write optimization rules. But we really do just to make what we send to the SMT solver very small so that we can prove bigger and bigger problems as we go. Proof reconstruction that we discussed a bit earlier. Proof reconstruction is really interesting because basically we will ask the tool to provide a proof that can be checked by lean so that we can now put the tool in the untrusted. We don't want to trust the tool that's producing the rules, because we will just trust the Lean kernel to check that the proof is correct. And even in our optimization rule that we're proving, we are going to use the tool to prove the optimization rule that we're using, generate the Lean rule so we don't have to, generate the Lean proof so we don't have to do it. And so, yeah, the untrusted tool will be used to prove itself and hopefully become trusted, but you don't even have to trust it. We still have to write the annotation language spec and implementation, because right now we do everything in Lean. So hopefully this is one of the last time you will see Lean if you want to use this tool. Our goal is very much to have everything about that in the back end. Just you specify where your UPLC is, what are the properties, and then we just take care of everything and just return the counterexample at a much nicer level. And we're building a VS Code extension. I just wanted to show you a few screenshots. The idea is, yeah, so you have your code on the left with your properties, and we're going to produce those counterexamples. So this is for a trace of execution where we get the values at each step, which is nice, but it's annoying to read. So we are building those traces of execution from getting them from the script context, from mostly the script context actually, and building those traces of execution to show you, yeah, on that trace you reach a state where something is bad, and hopefully that's much easier to read for the developer, because I don't think they want to see the raw output of the tool. Our timeline, just going to go very, very quickly. So Lean Blaster is available online. It's called Lean Blaster. The version I showed you is not the one that's on this repo yet. We have to push it, but it's on our private repo. It's going to be there very soon with the tactic and everything. So if you have, if you're doing some formalization in Lean and want to try it, well, probably not going to work because you're probably using a type we don't support, but I mean, you can always have a look at that. And all of the things that I mentioned that we want, we're going to try to deliver it in roughly a year. One reason is that we got funded by Intersect to do that, so we have to meet our milestones. And the other one is we're really excited to have that released. And thank you. Yes.
So that looks really impressive.
Thank you.
That's great work. I'm sure lots of people are going to want to use it. The one thing I didn't see on your timeline, which I think is going to be really important, is documentation. I mentioned this in part because we've seen other great tools.
No.
I said, show me the documentation, and they dump me into a GitHub with the source code.
Yeah, no, that's not documentation, yeah. So part of our...
Really,
yeah.
Really important for all of us to focus on this.
No, I agree. And actually, in all of our Intersect milestone, one of the acceptance criteria is, and that's audited and reviewed and everything, is that we have documentation for what we're delivering. So if we don't deliver documentation, we're not getting orphans. So we force ourselves to write documentation. No, it's not that, but for each of those milestones, so the reasoning core, the blockchain formalization, annotation language, UPLC bridge, we will have documentation, a state machine as well. Equivalence checker, it's not something we promised Intersect, but we think it's a really cool tool because you just give two UPLC and ask, are they equivalent? So we want to finish building that, and hopefully we will write documentation. And proof reconstruction, maybe some documentation, but it's going to be for more advanced power users that want to really modify some stuff, and not like developers. Developers will not have to see Lean, so. But everything else, yeah, documentation for sure.
Basically what you're saying is it goes without saying that we will produce good documentation.
Yeah.
But in this community, it does not. Please say it.
I mean, what I'm saying is we force ourselves to produce documentation.
And to keep it up to date,
Yeah.
Romain.
Yeah, that's going to be...
That's the hard part.
Yeah. So we are looking at ways to... Because if you give me just 1 minute, I can show you that in the, for example, the optimization rules, optimize, rewriting, I don't know which one is your favorite, prototypes. We have, for every optimization step, we've written a doc strings that explain what we try to produce. So for, once again, power user that wants to modify some of the optimization rules or want to write their own, we give them what we wanted, how we did it, and that they can modify. So for the first deliverable, where it's the reasoning core, we have those, all of the optimization rules documented, so people can go through them if they want. And then we have some more users-friendly documentation, like you want to use the tactic, this is the option, this is what it should return, and we listed some of the limitations. Yes, Anna?
Different question
Mhm.
is, how do you deal with built-ins, especially crypto built-ins?
Ah, okay. I was fine until you said crypto. So I can show you non-crypto ones, like integer. It's a simple one. So we re-implemented them, basically. We had to. I'm trying to go through the conformance testing suite to show that we implemented what is expected. The crypto ones are interesting. I mean, it's a way of not saying annoying, because we can't implement them directly, because the solver would just never be able to solve about that. You can't solve SHA with SMT solver. That's never going to happen.
Some simplification.
So, yeah, we want to axiomatize what they're supposed to be doing and try to be as specific as possible so that we can produce like the traces of execution you see make sense. But then we figured a developer that's going to, they're probably going to, because we're going to replace them with very simple times in maps or something, so it might be integer or some strings. And if I tell you, well, it hashed to 1 and you were expecting 2, you say, but no, that's not a hash, what are you telling? So we want to implement the real ones in Lean, or real ones. We want to re-implement them in Lean, or maybe use FFI to the official ones, so that when we do the trace reconstruction, well, the solver is going to tell us, well, I put 1 there, but we know it's a hash, so it doesn't make sense. And we will try to produce valid sequences of hash or signatures or keys, but everything will be abstracted on the proof side, so that we can reason about it. So we will axiomatize. We write optimization rules, like if you're verifying a message that was signed by the right private key with the right public key, we want to just simplify that to true. So we have all of these that we want to add to be able to reason about those kind of built-ins. But yeah, we have.
Having the concrete value.
Well, yeah, because we can't.
This is what I was going to say. Can you kind of axiomatize the actual property you need without the detail of it?
Yeah. That's what we want to do. And
the same thing will get the same hash. We don't know what it is, but we know it'll be the same thing.
yeah, and well, you might say, no, that's not true, because hash have collisions. But if we don't had that, I mean, the same way that the Agda formalization had to add it, the solver will just tell you, oh, I found a way to steal your liquidity. You just need to sign it with a key that just produced the same. And you're like, yeah, of course, but yeah?
Something I didn't understand. You said at the beginning of your talk, you have or you need icon to Lean and Plinth to Lean.
Mm-hmm.
But at the end, I see you're directly loading your UPLC code.
Yes, no, that's true. So we wanted to do that at the beginning, and we thought, well, UPLC maybe in the future. We decided to go the other way around, but we will still need some help from the compilers, because like if we end up using like a special comment tag to put the annotation in the code, when people will want to use the tool, they will need. Since we are supporting UPLC and only UPLC at the moment, then we need to compile to UPLC, but also we need those annotations that were removed by the compiler. So we need to figure out a way by anyone that's interested in having their language being able to use that tool to get us those annotations, like the properties you want about your smart contract, done somewhere so that we can also parse those and add them to the Lean files.
Okay. Another question then. Don't you think that if you have icons to Lean, for instance, you don't have all this burden of the C key machine, and maybe making proofs will be easy for the SMT solver, like regularly.
Oh, yeah.
Translation.
Yeah, so that's one thing. Okay, we have many ideas, but one thing we want to do yeah, as I said, we re-implemented the Plinth library. So you have not all of it, the cryptographic, not there, but like we re-implemented either is left is right, and what we want to be able to do. I mean, we're trying, as I said earlier, we try to be very one-to-one. So you should, if you have a function in the Plinth libraries or icon, but we just didn't do it for icon, you should have an equivalent one in Haskell. So we want to be able to that way move from Plinth to Lean. And one thing we didn't have time to try that yet, is we want to be able to see if we can prove that what you've transpiled at that level is equivalent to what the compiler gave you as UPLC.